When I choose this, when I choose you can see the text one. Okay.
He says, I'll look at the and is it true? Huh? Initial slides are there.
Yeah, we have said.
So this initial person same. The initial slide. Oh, initial slide. Then just to take about 5 minutes. We can start. Okay, yeah, good afternoon to all of you. In today's class, we will have a case study, and where you know that artificial intelligence is taking a major role in many aspects, in different aspects of engineering. So one such talk, they will try to focus on how AI can be used in air quality. Particularly, our course is mostly to look at air pollution and control engineering. We are also trying to see that how the different tools will be very useful in addressing the urban air quality problem. So I'm it's a pleasure to introduce Ekta. She's working in Queensland University, and she will going to share her experience. And she's also quite a she's a mathematician by training, and she is using AI applications in addressing the various different aspects of engineering. And one such our focus is on air quality problem in how AI can be useful in addressing the air quality problem. So before that, I also wanted to give a couple of things about our air quality management lecture series. And you all know that we started about 4 years back, and journey is good. And we all know that this is a question: how do we increase this number? So, but the other question always comes is: do we need increasing the number, or do we need people to work in this area with it? So I'm just looking at we will always look at you know close group to make sure that people work effectively and understand. Uh, Passion is something which you all do. You like to do the things what you like. Maybe that's where your passion comes. So I will try to look at it. Although we have seen that air quality management lectures series earlier we used to, so depending on the lecture, we also see that interest depending on the topic interest people will come, and today's topic is also much more interesting to all of you. I was just to the idea of this air quality management lecture series is to give you a platform. So, for example, in the current context, it is very important for all of us to connect. So for example, you have your own friend circle, you have your own friends WhatsApp group. And similarly, we wanted to create some kind of a group where the similar ideas and opportunities can be discussed. So that's one aspect of it where the professional members can interact, and they can bring a lot of collaborative and cooperation among them. So if you try to look at it in the past, we could able to reach out to all the experts working in air quality management areas, and so kind to all of them because in fact they've taken their time to share their valuable thoughts. And this air quality management lecture series also helpful to several students who are working in a project. They could able to connect with the speakers and get the PhD admission or get into postdoc. So there are plenty of opportunities that are with this platform is providing, and we are happy with that. So it's not only to make sure that you are listening to the lecture, but it's also helpful for providing an opportunity for the students to get and work with the various speakers. So if you try to look at generally we used to have on Fridays, and since this Fridays also became an holiday, so we just thought we will just move that talk to and this today. And thanks to that, Ekta also kindly agreed quickly, and she traveled all the way from Australia for some other official work, and in fact we could leverage our visit to talk something related to air quality. So I also when we started looking into that, they also mentioned the air quality management association. I don't know whether how do we see this kind of an association will be beneficial. For example, generally association will be beneficial for a little experienced people because they try to look at it more of opportunities. For example, the industry people will come, they discuss their problem, then there is an expert will be available, then try to see that how to resolve it. But I also thought this association should also be useful for students. For example, if the students wants to go to a particular industry to have some training, so that this association should help identify some key industries that are available and try to help them provide opportunities to go and work with that industry. Because this association will bring them a close interactions with many of the colleagues working in that area. So this will also provide an additional opportunity to that. And this is a 2-year-old association. And the other aspect I just wanted to highlight, and this is something which we have done wonderful work, because basically, you look at it, CEPHA network was a UK sponsored research project with Government of India and Government of UK. And this was very good because many more than 10 institutions across the globe are part of this. Several workshops internationally in Malaysia, Singapore, Thailand, and even in Australia. So we could able to make it, and that's sometimes it also have allowed go for student exchange. Some students visiting from other universities to India, and our students go and visit other universities. So this was useful, and basically we also try to see that sometimes that uh, every problem will not have a common solution, but a particular problem works in one place. Maybe probably we can learn from that and see that what modification, how it is going to useful addressing the similar problem in other places. So that's one aspect of it, and of course uh, we we started exploring in many aspects, looking into air quality management. So we started this Indian international conference on air quality management almost this year, which will be at 10th. So we attract many speakers, students to attend this particular conference, and there will be a winter school also part of this conference, and many students are getting benefited attending this particular conference. So now I'll request Lakshmi to introduce the speaker, and then I'll ask Ekta to start. Thank you.
Dr. Ekta Sharma is an early career research academy, currently serving as an Australia-India Women Research Fellow in the Department of Civil Engineering at IIT Delhi under the ECR Joint Fellowship Award in Air Quality, and as Fellow for the Higher Education Academy at the University of Southern Queensland, Australia. She is also a member of the steering committee for the Australia-India Research Collaboration Framework. She is a renowned researcher in atmospheric and space sustainability and has gained recognition for her innovative use of artificial intelligence in developing early warning systems and improving air quality. Among her achievements, she was the sole recipient from Queensland to receive the prestigious National Intelligence Grant from the Office of National Intelligence, Canberra, marking her contribution to significant strategic initiatives. With academic experience across Asia, Europe, and Australia, she holds a bachelor's degree and dual master's degrees in operations research and mathematical sciences. Dr. Sharma has applied her expertise to data-driven projects for the Australian Defence Science and Technology Group, the Office of National Intelligence, the Bureau of Meteorology, and Swiss Telecom. Today's talk is titled Leveraging Advanced Deep Learning and Satellite-Based Data for Urban Air Quality Management in Smart Cities. The talk will focus on the development of deep learning hybrid models for predicting air contaminants, demonstrating their effectiveness through testing in regions severely affected by pollution. The practical utility of these models in air quality forecasting for health risk mitigation will also be explored. We welcome you, ma'am.
Thank you so much. And next time I'll have a shorter bio so that we are done. So, Pranakam and hello to everyone. Thanks to Professor Shiva for the kind invitation and also to Professor Kare for initiating the talk. So, my name is Dr. Ekta Sharma, and a brief background. I'm originally from New Delhi, and my background was in operations research. So, I worked with University of Delhi for a couple of years before moving to Switzerland, and I worked with Zurich University of Applied Sciences. And then we moved to Australia, and I started my PhD in AI. So that gave me an exposure of how machine learning and AI is actually helping in different kinds of problems of air pollution, climate change, space satellite problems, how solar flares affect satellites. So that was a good exposure. So I started the talk, and before that, thanks to all the students for taking time to attend the presentation. So my lecture rationale will capture these points. I'll discuss the country's biocarbon footprint and some recent air quality facts. I'll have a case study based on Australian data. Why Australia has an air quality problems? What are the health issues? Because if you know, Australia is an arid continent. All the population is in the coastal regions, and the inside is quite dry, which is uninhabitable. So there is, and maybe you're aware of it, Melbourne is the allergy capital of the world. 1 in 4 people are affected by asthma or hay fever or pollen allergy. Some kind of allergy is there. And according to the recent statistics, people who are born overseas, they are 20% less prone to asthma compared to the people who are born in Australia. So Australia is one kind of example where you have the most cleanest air on the earth in Tasmania and Hobart, as well as the top hotspots because it's a mining hub. So if you go to Queensland or Victoria or maybe other parts, New South Wales, Port Pirie Centre, because of the mining regions and the coal facility, the air is quite bad. So I'll discuss one case study based on that. So this is a brief overview, and like we all know, there are several different kinds of pollution. We have sound pollution, light pollution, and the most common and prominent ones are the air and the water pollution. For air pollution, the main problem is the combustion of the fossil fuels like coal, oil, and gas. And the primary compounds which make up greenhouse gases are methane and carbon dioxide. And a major contributor is our carbon footprint, which is increasing year on year, and there is no sign of abating that. So, according to Intergovernmental Panel on Climate Change (IPCC), the concentration of carbon dioxide, methane, nitrous oxide, and other traces of gas have risen sharply after mid-20th century. And the global emissions have grown considerably after between 1970 to 2024, around 70%. And they continue to rise today, and there is no sign that they will decline or come down. So, according to WHO, the toxic pollution is among the leading risk of factors for non-communicable diseases. So this slide shows top 10 countries by carbon footprint. So generally we say that developing countries have a higher footprint than developed countries because of the industrialization. But other countries which are developed countries have had their industrialization in the 19th and the 20th century. So if you look at the population, we are not comparing apples to apples. The countries like Qatar or Luxembourg, they have very less population. Even Australia, the whole entire population of Australia is similar to the population of just New Delhi itself. So if we say that Australia is emitting less or having less carbon footprint, it's not a fair comparison compared to a developing country such as India or Pakistan or China, where the population is immense. So just for the fact for carbon dioxide, the rank of Australia is 14th. So this just depicts per capita emissions or deaths from the urban air pollution. And as I said, Australia is ranked third globally in terms of total carbon dioxide emissions per capita. And if we compare carbon emissions to the population, that equates to 15 tons of carbon dioxide per person, which is phenomenally high. And it's more than 3 times the average global rate, which is 4.7 tons per person. And also, Australia is the third largest exporter of the fossil fuels. So exporting 7% of the world's fossil fuels carbon dioxide potential. And we have bushfires also. So when we have bushfires, we have dust storms, and they are quite frequent, which adds to the problem quite frequently. And if you know, in 2019, 2020, we had the black summers, or because New South Wales and Queensland's air quality was really, really bad. So these are some Australian news clips. In Melbourne, if you know, in Victoria, traffic pollution, there is a student who was mentioning the vehicular pollution. So for Melbourne, there is an immense problem of the traffic pollution. It's a really big concern in the inner part of the city. And a quarter of the air pollution in urban cities is by higher emissions of the diesel trucks. So what happens is, the average age of truck is 17 years there, but actually the truck never dies. Like we have cars on say CNG or diesel. They have a specific shelf life. After 15 years, they are scrapped. But in the case of the trucks, they never die. They are never rolled into the hall of the scrapes, or they are never sold for the spare parts. So what happens is the parts are used in the new truck because the cost of a new truck is 250,000 Australian dollars, which is very, very high. So it keeps on recycling. And there was a study which studied, we have child care centers. Generally, the child care centers are near the main roads, and the carbon dioxide and the nitrous oxide concentration in the lungs of the developing children was phenomenally high, which were close to the main roads. So, which is not a good scenario because the next generation is suffering as the child cares are all along the main roads. So now I come to the particle pollution. Like US Environment Protection Authority measures 5 major pollutants, all of which are regulated by the Clean Air Act, which is carbon monoxide, ground level ozone, sulfur dioxide, nitrogen dioxide, and particle pollution, also known as fine pollution PM2.5 and coarse air pollution PM10. So of all of these, particle pollution is the most commonly studied or monitored, but it poses several challenges like three-dimensional movement of the air particles, which is very hard to capture. And also when you work on particle pollution, there is another challenge of the data. Whether you have a ground data, whether you have a satellite data, how to capture them, and when you are also studying the visibility which is associated with particulate monitoring, you can see that specifically around the airports, we have the problem of fog. In the morning or late in the night, especially during the winter season, there is a problem of the visibility, the planes can't fly. So we have another issue apart from the PM of the visibility reduction problem. So this is just a basic illustration that how thick is PM. It's similar to a human hair, and PM2.5 we all know they are from the organic compounds of the combustion particles. 10 is from the dust or pollen. So if anybody is working on a project related to health, then PM10 is of great significance. And today's case study is also based only on PM10. So my work is entirely focused on machine learning, then it evolved into deep learning, and then transfer learning, extensible AI, and now it's focused on reinforcement learning. So AI is evolving and will continue to evolve in coming years. Now with the boom of quantum technologies, if any of you does a course or a certificate in quantum and combines it with your AI knowledge, that is a very high demanded skill, not just in India, but globally. So why does it matter? Some of you must have worked on the deep neural networks or the neural networks, and it has gained the widespread attention due to several benefits. The benefits are your high forecasting precision, your non-linear mapping. These models are more efficient compared to our numerical models. There are some advantages, but there are some disadvantages also. They consume more memory. You need a GPU, otherwise, and you need a high performance computing laptops. Otherwise, they keep on running for days. So the computational time is quite high. The memory consumption is quite high. No doubt they have high forecasting precision, but there are some disadvantages. So we'll talk about how to solve the problem of curbing those disadvantages. So the first model we have is convolutional neural network. So if some of you have worked on deep learning or maybe have read the paper on deep learning, these are the base models. So I'll have 4 or 5 models and I'll just give a brief overview why they're important and when not to use them. So these models are very good for feature extraction. Like all of you might be on social media like Facebook or Instagram. So when you capture a photo, you capture the features. The phone also asks you, is this you or is this your family member? So what is it doing is it's capturing the features from your photo, tagging you and then mapping it back to the database. So what this model does is we provide them with the photos of say PM10 or PM2.5 or whichever whatever our sensors have captured, and then we pass them through these filters. So we will have convolutional filter 1, 2, 3, depending upon the need of our project, pass them through the coding layer, and then the model will be able to understand, okay, this is maybe cat or dog or whatever data we have passed through. So the advantage is very high accuracy. Very high accuracy in image recognition problems. So when you're doing machine learning, there comes a stage when you have only visual data. You don't have numerical data. So when you have visual data, these are the models to be used. They automatically detect important features, but they require human supervision. Another advantage is the weight sharing. Like it shares the weight depending upon the input you are providing to the model. The disadvantage is it requires a lot of data. 10,000 images of cat, 10,000 images of dog. And then only it's able to learn because it's not a human understanding. It's a program where you have to input the data a lot. So these are the advantages and disadvantages of these models. Then comes LSTs, long short-term memory networks, which are another popular and very, very, they have gained widespread attention because of their nature and their efficiency. It's a variant of RNN, which is a recurrent neural network. That's a family, and these are part of that family. And what they do is they have a memory mechanism. Like in the last one, we didn't have memory. We have to continuously supply them with the photos, images. Here, they have a memory mechanism. They have input gate, they have output gate, they have a gradient vanishing mechanism, which is another thing. So, they overcome a lot of problems which the previous models have. And they can process entire sequence of your data. Like if you have numerical data, like I have an example here. I'm not sure why is it not showing the full picture. It says amazing, the box of cereals gave me a perfectly balanced breakfast. So we have a whole paragraph there. So whenever you are working on a problem that has a textual data, you feed in the text like a book, and what it does is it filters out the most important keywords of that model. So that shows that we can use any kind of model based on the nature of the problem and what kind of data we have. So recurrent neural networks, I told you that is a whole family of which LSTM is a part of the family. Then we have GANs. So if you are studying air quality problems, GANs are very, very commonly used in the published literature. So what they do is, basically it's a class where we are feeding in the data. Like you might have seen there are a lot of viral clips of fake news. So what happens is they provide the video input, like if your data is in video form, they provide in the various videos and then the generator produces those videos, maps it with some audio or another video, morphs it or does whatever it wants to do, and then whatever the output comes, it checks whether the input is same as the output. So what it does is it basically filters out your fake news from the genuine news. So that you know that okay, if we have a pollen image, pollen is a major cause of hay fever or asthma. So you will only have visual data. But whether it's a genuine data or whether it's algae or fungi or other spores or whatever it is. So this is just a description. But I was working on a project with UQ and it was a very interesting one which was based on GANs. So what happened was they gave me a problem that suppose there is no life on the planet, even then the algae will survive. Okay, but algae and fungi, they are infested with rodents, the pests. So how to extract rodents from the algae so that we have clean algae? So what we are doing is we are supplying our models the whole adulterated samples infested with rodents and then separating out the clean algae with the pests. So that was the project. So that was the clear-cut example of a GAN model. So these are some other models which are commonly used if you wish to make a project in AI or machine learning. These are other commonly used models. The last one is autoencoders, which I will just mention that if, like in future, you go into a defense project or intelligence projects, they heavily work on autoencoders. So what they do is they error correct those models. Like they just detect the errors and then they make the sample free from the errors. So what is the difference between a GAN and an autoencoder? GAN is filtering, these are correcting. So earlier ones are filtering fake news from genuine news. Autoencoders are monitoring, classifying, checking, and then they are correcting the model. And I use them for Australian soldiers. Like you have a radio. The problem was we have a radio on the battlefield, and when one soldier talks to another soldier, and when they call on the phone, there is a lot of static that comes on the receiving end. So what I had to do was I had to use AI and do the signal processing, separate the static from the main component. So I heavily use my AI autoencoders. So this is just one of the practical example where such models can be used. So doesn't matter whether you are doing statistical models, numerical models, or AI models, you just have to know the application area. So the case study is based on those most polluted hotspots. So these are some of the most polluted hotspots in Australia in different states, and I have taken 4 main hotspots, and I'll tell you why those particular hotspots were chosen. So the case study is based on deep learning model. There was no ground monitoring data for this case study, and we studied only particulate matter, then post particle pollution in 4 main hotspots, and we used machine learning to forecast the air quality for the next hour. I'll discuss what all satellite variables are used, why they were used, what was the importance, what was the model that was used, and I told you CNN already suffers from some of the disadvantages. So I merged it, or you can say integrated or fused it with another model to overcome the deficiency and handle the potential of the non-linear feature mapping with precise forecast, because that was the objective. We had to forecast the next hour's air quality. The main novelty was early warning scenario. Like if you have bushfires, can you predict in advance that maybe the next month there is a high probability of bushfires? So if you can predict in advance and the prediction is true, then the model is successful with the right kind of data. So to explore the merits of the proposed hybrid model, which was a deep learning model, in the hourly forecasting, I had 4 hotspots. So if you look at the southeast, Australia, we have Queensland. So my university is based in Queensland. We had Mount Isa. It's a prime mining hub, most polluted postcode of Australia, Mount Isa. We have Hunter Valley in New South Wales. In Victoria, we have Latrobe Valley. And South Australia, we have Port Pirie Smelter. So this was the study area for this case study. Now comes why the hotspot were chosen. So whenever you do any project or any kind of, you write any kind of research article, it's very important to justify why you have chosen that particular study region. Because you need to have a useful research which can be reproduced by future researchers, like they see your work, they use your data, and they are able to replicate the same amount of results what you did. So these hotspots like Latrobe Valley, it has higher than state average of healthy years lost due to health issue caused by PM10. We have the largest coal-fired power station. We have a paper mill. We have open cut mines. So it's the third largest emitter of PM10, emitting more than 30 toxic substances. Mount Isa, I told Mount Isa is the most polluted hotspot. The main problem is the zinc mine, the copper mines, and the lead mines. So the asthma mortality, which is very, very staggering high figure, 322% more than the average rate of any person anywhere in the world. So it's actually not inhabitable. Whoever is living close, and normal people can't live in those areas. What happens is people who are working in the mines, their families are living, their children are living. So the pay is very high, but these are the problems which are not curable, which are happening in those areas. So when the study was conducted only on young children, 11% children had elevated blood lead levels. Hunter Valley, why it was chosen? Because we have a lot of coal trains, we have a lot of coal facilities there, and the particular matter pollution 10 course 1 was 171 times in previous years in Hunter region. So if you just Google Hunter Valley problem, it will come up. Highest blood lead levels in people who are living there, and it's a very vast region. It's not like one town or one suburb. It's a vast valley. So it comes heart disease and lung disease are very common. Then there are smelters. Port Pirie smelter, that's the different state, South Australia. So it has the largest sulfur dioxide and lead smelter, biggest in the world. So we have more than 1,000 times sulfur dioxide problem since 2003. So if you see, all of these stations have had studies done on young children, and all of the young children have elevated lead levels, which is a major concern. And government won't shut them down because it's a prime source of money or funding for the government. So it's very hard for the government to shut down such projects which are happening in the area. So the data is from, majorly it's the satellite data, which is from NASA Giovanni. I'm not sure whether the data is available right now because of recently lot of satellite data have shut down. So either they are paid or the amount of data which was available earlier in the times, that amount is not available. So these are all the sensors which I used for these data: Terra sensor, air sensor, OMI sensor, and it was downloaded from the NASA website. For ground data, generally what I do is whichever hotspot I study, I contact the government which is responsible, or the authority which is responsible for environment protection there. I contact them and I get the data from that specific authority. Like for Queensland, I have Queensland Government Department of Environment Science, or for South Australia, I have EPA, Environment Protection Authority. Same body is also for Victoria, and the New South Wales have their own. So that's how I get my ground data and satellite data. All the data is regularly monitored for their quality check. We can't use the data which is having a lot of missing data. So I'm not sure whether how much missing data you take in your projects. Is there a percentage you follow? Like in your papers when you do the research. So when you capture the data, how much missing data is allowed for any kind of modeling? Standard?
Generally use 10%.
10%, right? That's a standard, that's a published norm. So if we have more than 10%, we generally discard that particular hotspot. So how do you take care of the missing data? Do you do averaging? Interpolation, right? That's another commonly used way. So people do averaging, people do interpolation. The point is to take care of the missing data. So this is just a geographic description. So whenever we have to use machine learning, it's very important for us to understand the results and why those results happen. Like for example, if a site is very elevated, was that a reason that it had less PM 2.5 concentration or vice versa? What is the longitude, latitude, and then we are taking care of the missing data. And we encourage to divide the data not just in training or testing, but also with validation. So the standard generally is, there is no standard actually, how much percentage you need for training data, how much you need for the testing data. But from the guidelines, what we have seen in the published literature, at least 60% of the data goes in the training sites. Or some people also use 80-10-10. 80% training, 10% validation, 10% testing. Some people use 60% training and rest goes into validation and testing. So that is not a norm, but just a practice which the published researchers are using since long. So these are some of the points we always take care before we start AI modeling. So we check whether we are dividing or subcategorizing the data into training, validation, testing, and not just training and testing. Because when you take validation, it fine-tunes the data, right? So all of this division is done before testing to remove the bias of dispersion of training as well as validation test over the training subset. After the model execution, whichever model you wish, like numerical model, statistical model, or AI model, the important checkpoint is on the training set. We do a lot of statistical tests, which I just glanced through. We check what kind of errors we are getting. If one particular set is giving us a lot of errors, that means the site is prone to a lot of errors. It's not a good data, or the site needs to be changed. So we do our data processing, and the variables which I took, ground plus satellite variables, were I think 53 or 54 variables were taken in this case study. How much variables are there? 30. 30 variables are taken for this. So if you see, I have to go back. Yeah. So of all the 30 variables, see what are the variables which are chosen? Dust, cloud, low clouds, middle clouds, water vapor, wind speed, ozone, temperature. All the variables are chosen. However, some variables are depicted in red color. That means those variables were selected for this study and other variables were discarded. So how do we know which variables need to be selected and which variables need to be discarded? Other columns just show the sensor which was used, the spatial resolution, and what platform was used for the satellite data. This is just to enable future researchers, in case they want to replicate the study and involve more hotspots, they know what data was used. These were the other variables: methane, carbon monoxide, nitrogen dioxide, sulfur dioxide, aerosol absorption. But they were not chosen for modeling. Reason being, how do I know whether temperature is important for Portland spectrum or not? Whether weight is important for Mount Isa man or not? So these are the steps we do. We either do cross-correlation of my predictor variables with the target variables. Target means I want to Suppose I want to forecast nitrogen dioxide. So that becomes my target variable, and all the 29 variables become my predictor variables. So I perform cross correlation, which I think you might also be doing, of the between both the variables, and then I see whether that is significant or not significant. Also, I do partial autocorrelation, which comes here. So when I do that for all the variables, I just see which variable has a significant lag with respect to my target variable. And I select only those variables which are important. Dash means that particular, like we have dust. I think the first variable is the dust. Then we have cloud temperature. So that does not have any units, so that's dash. Other variables, what the units are depicted within the brackets. So this is the cross correlation, and that one is the partial autocorrelation. If you are forecasting 1 hour, I take 1 lag. If you are forecasting 1 day, 24 hours, I take 24 lag. So this is just a heat map. I always involve one kind of figure for a person who is not very comfortable with the modeling approaches but interested in the quality. So heat maps are another visual way of depicting which variable was significantly important for the study and the data. The darker the color, the more significant that variable is. And it varies from -0 to 1 or minus, depending upon what kind of relation you have, whether you have positive correlation, whether you have negative correlation. So this is for all the 4 states, New South Wales, Victoria, Queensland, and South Australia. So this looks very complicated, but actually it's not. It just depicts in a single illustration what was done in this case study. We had both the variables, ground and satellite. We processed it with data pre-processing, missing data checks for validation for the quality of the data. We filtered more than 10% of missing values. We did our degree check, which variables were important. And then we had 4 different sites. We used a convolutional model, 3 layers of the convolutional model to filter the features, and then we combined with the gated recurrent unit model because if I just use one model, the deficiency or the limitation is it uses a lot of data. I can't afford to provide 10,000 samples just for one variable. So I combined it with the gated recurrent unit, another machine learning model, and then I finally forecasted the PM10. However, in the funnel, if you see, I have used 3, 3, 6, 7 models. So one is my main model, and I benchmarked it with several other models to see whether the main model is actually good or maybe some other model is performing better for other sites. So whenever our paper goes for publication, generally reviewers ask for the architecture which is used for all the models. So it's always good to supply that when you were doing modeling, what was the architecture used. So epochs, like I'll just take the last one, GRU. How many iterations you did? 500, 10,000, 1,000. You have to tell the reader, like it has to be a transparent approach. How many iterations you did? What are the activation functions you used? And that size. So if you see, there is one model on the top which has some red values. That shows at that particular point, the model performed the best. So I always keep my main model on the top and other benchmark models on the bottom. And whatever the model uses, those are depicted on the right hand side. It's kind of like a grid search. Rest of the models and their approaches and the entire architecture. So suppose any of you wishes to carry forward this approach, maybe for some other country, not Australia, some other country, you know how I approach this problem. You can just pick the most optimal ones. You can just pick, and then from that stage you can carry forward your research for some other country. So that's the whole purpose of including such architectures. So this is the statistical evaluation. So it depends whether a person is more comfortable with. Is it high enough? No? Okay. So if a person is more comfortable with a statistical approach, they can just carry these models. But if machine learning is involved, then we have to compare both the models. So these are just the benchmarks to test different kinds of results. So when I work on any model like this, I would also suggest for you as well, whenever you are writing papers, whichever model you use, whichever numerical approach you use, always reuse the formulas as per your own requirement. Like for this, because it was particularly matter 10. So this is forecasted PM10 for ith point. So these are my own variables. So you can use the entire formula. The formulas are standard. They are not like I did not invented those formulas, but notations needs to be your own. Otherwise, you have to provide the source if it's going in a very high impact journal. So this is something, if you don't do, you can adopt that approach. That really helped me in differentiating my work with other researchers. Continuing these, so I have at least 6-7 models all the time in my papers to see whether the model is actually beneficial for the project or not. And similarly, I test with 6-7 error approaches. What is my mean square error? What is my bias error? What is my correlation coefficient? To check. So these are just the performance metrics to validate your model. Wilmot syntax. Nowadays we use Leggett syntax also. Coefficient of variation. So these are just some of the results for different sites. Like first one is for Queensland, then New South Wales, South Australia, and Victoria. So the red one depicts the same model which performed best, but if you see this one, the third site, CNN LSTM has performed better as compared to the main model. If this model would have performed better for at least 3 sites, I would have picked up this model for this kind of data. But this does not mean that CNN GRU is the best model for all the projects, for all the scenarios, for all the data. For these hotspots, it worked well. Maybe for some other hotspots, these don't work well. So generally, hybrid approaches are followed these days. But when I was doing my defense work, surprisingly, this model performed the best. The simple, no fusion, no nonsense, pure model performed best in all the data. So the data was different, it was self-generated data. So even sometimes simple models perform best depending upon the kind of problem we have. So rest of the slides are just a few visual metrics. For some reason, they are not coming proper here, but I can see they're okay here. But anyways, these just depict the testing performance of the main model compared to the rest of the models. Again, 3D bar graph of the root mean square. So you'll just see that, it's temporal data. And if the root mean square is less than 5% or the mean absolute error is less than 5%, that puts the model in the more excellent category compared to the other models. So this is just a stack column chart for the proposed model for different sites. So the benchmark models will perform between 0.32 to 0.62 for Queensland, 0.21 to 0.35 for New South Wales, and then rest of the models. So this is something which was asked to me by a reviewer, that you are using deep learning models. It uses a lot of memory. What is the testing time for each model? What is the cost involved for each model? So I had to run the models again, note the time for execution for each of the model, for each of the parameter, and then I had to depict what was the loss involved, like how much training loss was there, how much validation loss was there, because it's a penalty for a bad prediction. We are forecasting our air quality, but what is the penalty involved? If we are forecasting poorly, there has to be a fine or penalty involved. So, how do we measure that penalty? Because in models, modeling approaches, time and cost is, time and memory is the cost of the project. If your model is running for 5 days, then it's not a good model. Or if it's using 5 GPUs, it's not a good model. Then there is no efficiency. You need to have efficient models. So with advancement, efficiency needs to be there. So this is just showing the inference time, and the line chart is showing the average inference time in seconds for the data with a test batch size of 100, not 50,000, but 100. This is for the state of Victoria, and the lowest inference time is of 2.6 seconds for our model. So the next best model we had was CNN LSTM. It had 3.9 seconds for a batch of 100. So this is another question asked by, this was another question asked by the reviewer. What was the memory used? So it's a stack bar chart showing the comparison of time, cost and memory consumption of the various models used in the study. So time per epoch refers to the average training time per second per iteration. And what is memory? Memory is the memory consumption of in megabytes. So coming to the conclusions, the proposed architecture, because we get the errors below 5% for that particular model, we put that in excellent category. But for the rest of the models, because it was more than 5%, they were not as good. The tools developed, the deep learning tools were tested for computational efficiency, time consumption, and memory usage. And we tried to bridge the gap in modeling coarse particulate matter with a diameter between 2.5 and 10, with the impact on evaluating the potential of ground and important satellite, 30 satellite-derived predictors. And of course, we compared it with statistical performance metrics, visual metrics, general data. As I said, every model has their disadvantage. So what was the limitation of these models? So generally, the computational model, like from OpenAI source, the computational power to train the popular AI models has doubled every 4 months since 2012. So the process involves a lot of trial and error. Like as you have seen in the optimal architecture, I had to start with 50, 100, 200, 500 till the time I reach an optimality. If I don't reach an optimality, I have to stop somewhere. So a lot of human involvement is also required. A lot of data is required. So these are some of the major limitations of machine learning and deep learning. Yes, they are good, they are precise, but they have their own limitations. I'm not going to overcome the challenges. So I talked to a few students in the morning. I am here as an Australia India fellow. So one person from Australia, me, has come and visited India for 4 weeks to 6 weeks. We have to work on projects of air quality, and one person has gone from India to Australia to work with a similar university on a different problem, maybe water problem or a satellite problem, or depending on the project that was funded. So this is a bilateral agreement, and it's very good to see that these agreements are already in place with UK, with Australia. This is such a phenomenal network. I was very happy to talk to Professor Khalil. I'm working with him since 2 years. We have published quite a few papers, and now we are extending the collaboration. So the main purpose of extending these collaborations are, yes, we intend to solve the problems which are of strategic importance, SDG goals, but it's also intended to help students, to enable students to explore opportunities in different countries, to explore, to have a new flavor of different problems, like I gave you the flavor of the different hotspots of Australia. Because if you talk to a common man, generally they say Australia's air quality is phenomenal. But that's not comparing apple to apple. The population is very less. Still, there is a high carbon footprint. There is a high rate of asthma, high rate of hay fever. Melbourne is the allergy capital of the world. So let's work together. And if any of you wishes to collaborate with me, you can contact me on LinkedIn. You can take advice. If there are women researchers, I have not told this. Since 2018, I started a non-profit, especially for the upliftment of women. And what we do is we started with 5 women when I was in Switzerland. And we started publishing books, non-profit storybooks. We all contribute one short stories. And the sale of these books come on International Women's Day every year on 8th of March, since 6-7 years now. And we have published 9 books during this period. And the sale of these books help in women with domestic violence cases, or refugee women, or maybe children who can't buy school supplies or art supplies. Or like recently we helped a school in Nepal where the school said that we have enough resources but we don't have a playground for children. So we diverted the money we got from the sale of those books to those resources. So this was like something which I really believe in. Like this is the skill you develop over time. But if you wish to be involved in any female-oriented research projects, like I came on an Australia-India Women Researcher Program. So women are welcome because of the diversity initiatives. If any of the females here wishes to talk more on the research, what are the ways, what are the options for us, I'm more than happy to help. You can connect with me. Whatever I know, I'll try my best. So feel free. And thank you once again to Professor Shiva for the kind invitation, and thank you all of you for your time. Any questions?
No questions?
For individual model, the hyperparametric tuning is also in the figure. So we have demonstrated that the CNN GRU is performing the best in this.
Yeah, for this kind of data. Yeah.
So is it a possibility to come up with some other tree models for integrating with the CNN?
I worked with random tree models, lot of M5 tree models. So that was the start of my PhD. Like, AI evolves all the time, but it does not mean that the benchmark gold standard models are bad models. No, there will be gold standards all the time. But it's just that because the technology is advancing, we try to benchmark them with the conventional models. So I still work with these models. It's just that for different papers we try different models. Yeah.
Any other questions? Yeah, maybe one question to me. So since AI requires a lot of data, so we also try to look at it, how much data in terms of data points. I'm trying to look at it.
Yeah, I generally take 3 years data.
3 years.
3 years data, so it's an hourly forecast and I end up with 32,000 points or 40,000 points. But if I know that the agency will not provide me with data, then it's a big problem. Then I can't do machine learning at all. Because like I told you in the Anki project, we were just provided with there was a lake and we were provided with 5 samples. You can't do machine learning in that. There are ways, there are data augmentation techniques which you can use, but then the results are flawed. Then there's no point using machine learning. Then go with your conventional approaches.
So any other questions? So,
Few questions in the chat.
okay, the chat box.
Are you planning to do research on this?
Yes, absolutely. It's going mental anxiety. The impact of pollution on mental health, anxiety, this is already going. And we work on dyslexia. The paper is in with the reviews right now. Dyslexia, COPD, mental health. That's a very big area. Very nice.
One more question. So how did you determine the lead content in humans?
What content?
Lead.
Oh, the hospitals provide us that.
So they asked whether is it correlated the lead content in the air.
No, that's a good thought process, and I'll work on that. Yeah, that's a good question.
Another question is, have you checked with the hospital based on cancer percentage?
No.
The lead levels?
Cancer, I am not checked, but it's because this is such a huge area, like one person in doing on particular pollution. So it's such a huge area. Cancer, I have not touched till now, but maybe someday, if any of you is working on a project, maybe we work together. So, but it's a very good. That's it.
Okay, the no other questions. I would like to thank Ekta for taking our time to give a wonderful talk. And thank you all. We thank you very much.
Sir, can we have a group photo?
Just to be there, and maybe Vijay can take it from this side. You come. We'll take it from this. Thank you.
I forgot I have this mic.
Vijay, will you go to
I'll share the filters.
Coming?
No, this is
Okay, comments. We can cover. Okay, switch off that. That should be okay. It should further. Okay? Yeah, thanks.
Thank you so much.
Hey, thank you all. Yeah. Enjoy your lunch. Meet Monday. Friday is holiday. So we'll meet on Monday. See you Sir, we carry on. After I saw your message. We can discuss it after. Huh? Okay, can you one side? We can ask them to come to this also and take it to the process. Here only, yeah? Okay. So I want to discuss, actually, she's interested in what exposure. And area is also to set for and push up to look at it because more data.
Yeah. I think it's starting my project next
Next,
semester. Okay, so you're a master's student?
Yes.
Okay. No, I'm happy to help her in any ways possible.
Sure, I'll just.
You can share my email ID with her.
Sure, I'll just introduce.
Yeah.
We will take it further. Maybe
Absolutely.
Poland are something which I was trying to
Yeah, we are working on a project.
So we try to look at it because that's what we are trying to do. Gallery something can be worked out and then we can look at it.
Anytime. Sir, I'm very helpful and supportive in that, that Professor Khare must have told. And there is a bias with India, where whichever country I work in, I keep coming back to India. So, yeah, anyways, I can help you.
Sure. Thank you.
Thank you.
Thank you.
So, we are going to the gap right now or what?